stops you, but because the universe simply gives you no path back out. Once you pass the event horizon, returning to the outside world would require traveling faster than light, which is impossible. From the outside, an object falling into a black hole appears to slow down, dim, and freeze in time. But from the falling object's perspective, nothing unusual happens. You cross the boundary without noticing. No flash, no distortion, just a one-way trip. Near a black hole, time itself begins to break. According to Einstein, gravity affects time. The stronger the gravity, the slower time moves. Near the event horizon, time slows dramatically. Right at the edge, it nearly stops. If you could hover safely near a black hole for 1 hour, you'd return to find that hundreds or even thousands of years had passed in the rest of the universe. You would have aged 1 hour. Earth would have aged centuries. Inside the event horizon, time becomes so twisted that moving forward in time is the same thing as falling inward. Once you begin falling, no matter how hard you try, every direction leads deeper. This depends on the black hole. If you fell into a small black hole, you'd be torn apart almost instantly. This process is known as spaghettification. Gravity at your feet is dramatically stronger than gravity at your head. The difference stretches you like a long noodle, pulling atoms apart. But if the black hole is supermassive, like the one at the center of our galaxy, the story changes. Because the black hole is so large, the gradient in gravity is gentle at the event horizon. You could fall through without feeling anything at all. No stretching, no ripping apart. Only once you get deeper inside would the increasing gravity begin tearing matter apart. The singularity, a point where our laws of physics break down, where density becomes infinite and space-time curves infinitely inward. But here's the truth. Nobody knows what really happens at the singularity. Our current physics simply cannot explain it. Some theories suggest it's a point. Others think it's a ring. Some physicists believe the singularity may even connect to another region of space-time, a wormhole, a new universe, or something entirely unknown. To understand the center of a black hole, we need a new theory, one that unites quantum mechanics with gravity. In 1974, Stephen Hawking made a shocking discovery. Black holes aren't perfectly black. They slowly evaporate. At the edge of the event horizon, tiny particle pairs constantly appear due to quantum fluctuations. Normally, they destroy each other instantly. But near a black hole, one particle can fall in while the other escapes. The escaping particle becomes radiation, now known as Hawking radiation. This means black holes lose mass. They shrink very, very slowly. Eventually, after trillions of years, they vanish completely. Even the mightiest black hole is temporary. Black holes are not just cosmic monsters. They shape galaxies. They influence star formation. They warp space-time across vast distances. And they may help us solve the biggest mysteries in physics. Black holes test our understanding of gravity, time, quantum mechanics, the structure of the universe, and the nature of reality itself. Studying them brings us closer to answering questions like, what is time? What is space? What happens at the limits of physics? And why does the universe exist the way it does? Black holes challenge everything we think we know about the universe. And as we learn more about them, we don't just understand black holes better, we understand reality better. If you enjoyed this explanation, subscribe for more science, 1 second at a time.